All right, thank you everybody for staying for our second and final session of Lightning Talks, which again presented by the Unique Student Affairs Committee, which is to showcase work done by students, members of Unique and the NeuroAI community broadly. Without further ado, please welcome Soufiane Bahari.
Hello everyone, I'm Soufiane Bahari. I'm a PhD student at University of Sherbrooke. And I came here to share with you some of my recent works on using some fundamental mechanisms of the inner ear to improve the speech processing in AI systems. So here I tried my best to draw the cochlea or the basilar membrane. Well, let's say that this is like the basilar membrane. The way the brain converts sound into a sparse representation is that through the vibration of the basilar membrane that would cause some changes in the potential of inner hair cells, and these cells will be activated in a sparse manner to represent the signal. But there is some feedback from different regions of the auditive system, from the audio cortex down to the brainstem, ultimately to the cochlea. So here it's the feedback from the log system that has an effect of lateral inhibition on the response of inner hair cells. And this effect actually makes the system more selective to the frequencies. Even though if you look at the receptive field of each inner hair cell, we found that the bandwidth is kind of large, but the whole system with the lateral inhibition is more selective. So here things got messed up, I guess, because the presentation, like transferring from Mac to Windows, things get messy. But here is the mock system. It's another kind of like feedback that acts on the outer hair cells, and this modifies the stiffness of the outer hair cells, and this effect actually protects the basilar membrane from very loud sounds. But it is also hypothesized that this kind of efferent signal actually acts on the sensitivity, acts on the sensitivity of inner hair cells. So our goal is to take into account all these aspects to build a coding scheme. So we have an audio signal, and we want to end up with something like this. We want to transform this input signal into a time frequency representation that is very, very sparse. So we start with a couple of units that have certain dynamics. They would do some computations, and we want to consider their activation as the representation that we want to end up with. So our goal is, from the activation, we want to be able to reconstruct the input signal as reliably as possible. Under the constraint of sparsity. We want that the majority of the units to be quiet, only few that represent the signal. These goal and constraints can be expressed by this objective function. It's a combination of the MSE error and a sparsity cost that can be an L0 norm or an L1 norm or whatever. So here, for each unit, we defined a certain receptive field it's a filter with a certain central frequency and certain bandwidth. And the projection of the signal into this set of filters would be equivalent to the vibrations of the basilar membrane that causes the inner hair cells to be activated. And the second aspect that we take into account is the lateral inhibition. The weights of these lateral connections are the correlation between the filters. That means If two filters are very similar, the inhibitory weight between them would be so high that if one of the two is activated, it will send a strong message to the other one to tell him, well, stay quiet, I'm already activated and we want to reduce the redundancy since we look alike a lot, so just stay quiet. So here it's the dynamics of the each unit. It's a leaky integrator dynamic. And it has been shown that this kind of dynamics are negatively proportional to the gradient of these objective errors. So this error basically is backpropagated to the dynamics of the units. So what we propose here is to continue this halfway backpropagated error to reach the receptive fields and to act on the receptive fields, because we are assuming that the efferent connection from the Mach system are affecting the receptive fields of the inner hair cells. Yeah, so we have some modulation parameters to control how each filter is sensitive around its central frequency. So we tested this in using speech. We have 3 cases. The first case, we use only the lateral inhibition connections. The second case, we use also the blue gradient flow that shaping the fields, the receptive fields. And the third case, we allow this gradient to act on the central frequencies. So basically, we also affect the distribution or the resolution of central frequencies. And as you can see, so the SNR is the signal-to-noise ratio. We measure by this the quality of the reconstruction quality. So including the adaptation, we have an increase of 3 decibels, and when we activate also the adaptation of central frequencies, we have like more than 5 decibels of increase, and we are able to do this with less coefficients representing the signal. So we tested this in a classification problem. We have spoken digits. We have 20 classes in total. And we have a classifier neural network, spiking neural network. It's a reservoir containing 124 neurons. And as you can see, the performance of the adaptation actually doesn't affect negatively the performance of the classification. However, plus that, the dynamic power per inference is significantly reduced. We implemented this on neuromorphic chips, the Loihi 2, and we were able to decrease the power consumption by 5 times, including the adaptation. And for all the cases, there's a big difference between the power consumption between the Loihi 2 and the GPU. The reason for this is that generally when you use neurons, deep learning neurons on GPUs, whether the input is 0 or some value, the neuron will do the computation. However, on neuromorphic chips, if there is no activation, actually there is no synaptic operation. So there are some other interesting results. For more details, come and see me. My post is on the board number 4, and thank you.
Thank you very much. Thank you very much, Soufiane. Next, we'll welcome Alicia Muniz Jimenez.
Hi, my name is Alicia Muniz, and I'm going to present. Sorry, I'm nervous. Okay, and I'm going to present the results of my undergraduate research project, which was co-advised by Dr. Victor Millangos and Dr. Arturo Bouces. Okay, anxiety is fundamentally an anticipatory response to uncertain future threats, meaning it involves a multi-step process. However, most of the computational research that has been made focuses on one-step task where an agent performs multiple trials of the same task, but each trial ends with just one single action. These studies have identified that an elevated learning rate is a key component to model decision-taking in anxious individuals. However, this contrasts with recent research that uses sequential evaluation tasks that has identified an elevated punishment sensitivity parameter to be K to model anxiety-related behaviors such as avoidance, threat overestimation, and generalization. Another key distinction between these two approaches is that while on the first one, agents learning relies on direct experience within the environment, on the second one, relies on offline planning. We wonder what would be the impact of punishment sensitivity and learning rate on an agent that performs both, learning through direct experience in the environment, but also that performs planning in a sequential evaluation task that is more close related to real scenarios. Okay, so in order to address this question, we developed two models, each focused to test one of the two hypotheses to see the role of punishment learning rate of punishment sensitivity parameter, and use them on artificial agents that perform the cliff walking task. The objective in this task is that the agent has to manage to get from the initial state to the goal, where he received a reward of 1 point, but avoiding to reach an aversive state, the red ones. Each aversive state gives to the agent a reward, a negative reward of -1 point, and also ends the episode. Okay, what is interesting here is that the environment is deterministic. It has stochasticity. It was stochasticity on the action selection of the agent, not just in the learning phase, but also in the testing phase, because we wanted to mimic that an agent lacks a complete control of its own actions, because this is more closer to real situations. Okay, after 100 episodes, we used the estimates of each state to make these heat maps, where a state that is on dark red, that red means that it has an estimate value that is closer to -1, while a state that has a blue color means that it's closer to a value to 1. Okay, the result shows that heightened punishment sensitivity plays a crucial role to treat overestimation and generalization. As you can see, that an agent with that characteristic estimates most of the states in the environment as dangerous, even those that are far away from the aversive states. Also, in contrast, we can see that elevating the punishment learning rate doesn't make a change in agents' behavior compared when the reward and punishment learning rate were equal. Unlike previous findings, sorry, I'm very nervous to read my conclusions. Like previous findings, our results suggest that the key factor is not how quickly punishments are learned, but the impact they have on planning. These results differ from those observed in one-step tasks, highlighting the importance of studying anxiety in contexts that are closer to real life. Doing so can lead to more accurate inferences about anxiety mechanisms. While testing these models in non-deterministic environments is important for future studies in sequential evaluation tasks, this first requires a better understanding of how individuals with anxiety construct a model of the environment, and also better understand their planning process. Thank you for your attention. If you have a question or want to know a little bit more about the project, you can see me on poster 35. Thanks.
Thank you very much. Up next, we have Yuan Song.
Hi, everybody. My name is Yuan, and I'm a PhD student at Université de Montréal. And I'm going to talk to you. I'm going to talk to you about using unsupervised learning to uncover non-motor subtypes progression in Parkinson's disease. So when we think about Parkinson's disease, usually we think about tremors or rigidity in movement, right? But what we don't know is that Parkinson's disease also comes with non-motor symptoms. Non-motor symptoms include symptoms like mood disturbances or sleep issues or pain. And usually they would predict, they have been shown to predict cognitive decline in PD. So when we know this, we could think that knowing better how to understand non-motor symptoms could help us understand how cognitive decline evolves in PD, right? But PD is a heterogeneous disease. This means that different patients could present with different sets of severity symptoms and different progression rates of symptoms, right? And in this case, unsupervised learning can help us study those progression patterns and could help us reveal subtypes of PD potentially, right? But the thing is, when we want to look at disease progression, usually we would need longitudinal data for that. But there's a new algorithm that came out recently called SUSTAIN. And that algorithm uses cross-sectional data. And it helps us predict the different patterns of disease progression. And so our objective here was precisely to identify those distinct progression patterns in PD using cross-sectional data of non-motor symptoms. So how did we do that? We used a data set called the Canadian Open Parkinson Network. And this data set comprises cross-sectional data, tabular data, right? That was measured using the MDS-UPDRS, which is a questionnaire measuring PD symptoms. And for the learning phase, we used a SUSTAIN algorithm on the data set to try to uncover the different clusters. And once those clusters were identified, we used multinomial and regression, ordinal regressions to try to compare those subtypes to see if they were in fact different. Ooh. Okay, so first, socio-demographics. So the sample we used was roughly just a bit about 1,000 subjects, of which 66% were male, and the median age was 67 with the median disease duration of 6.6 years. So we were able to identify 3 clusters, or 3 subtypes, if you will. So the first subtype here, which we call the apathetic one, showed characteristics like a lower prevalence of apathy, but a faster progression of apathy compared to the other subtypes. And so on for the mild motor predominant subtype and the cognitive subtype. So now that we have those 3 subtypes identified, let's look at another way of representing those results. So at the predicted PD onset. So at the predicted baseline by the algorithm, we can see that for the different symptoms, the different subtypes identified, they differed in gait, apathy, and hallucinations. Right? And another way of looking at this is to look at the association between the predicted severity, disease severity, and the actual disease severity of the patients. So we can see that for the actual disease severity of patients, the algorithm predicted a strongly coherent disease stage. So this is a good sign that the algorithm is doing its job correctly, right? So now we have those results. What can we do with them to make sure that they're robust and valid and stable? So this is precisely where we are right now, because we have results that seem to be clinically, that make sense clinically, but we have no idea if we would be able to reproduce them. And we actually started looking at this by testing the stability of those results by playing with the number of iterations we would run the algorithm for. And so surprise, surprise, we are learning that the results are not stable at all. So the next steps for us would be to try to find a way to see how those results, how we could achieve stability with those results so that we could confirm that the subtypes that we found are coherent, right? If you guys have any input on this, I would be very happy to chat with you, because this has been an issue in the past moments. And thank you for your attention all.
Thank you very much. Up next, we have Jinani Suryarachi.
Hello everyone, I'm Jinani Suryarachi. I'm a PhD candidate in Dr. Curtis Baker's lab at McGill University. Today I'm going to talk about the cortical state effects on responses of early visual cortex neurons. As you all might know, neurons' response to repeated presentation of the same stimulus is highly variable. Here you can see 2 example neurons and their responses for a natural image movie that we show for 5 seconds. And across 20 trials for the first neuron, you can see the response is slightly variable. But for the second neuron, the responses are highly variable across the trials. And for a population of 154 neurons, we saw that a majority of neurons' response are like the second neuron, which are variable across trials. But what was done previously is that just to take the trial average response and consider that as the stimulus-driven response and use that in the models that we develop. But when doing so, we can lose a lot of information about how this neuron carry on the visual processing. So it's important to understand why this variability occur and account for that in the models that we develop. So there are previous work showing that the reason for this variability is due to the brain state changes, which can vary due to many factors. For example, attention, sleep cycle, or anesthesia can change this. And even now, if you're paying attention or if you're feeling drowsy, your brain can operate in different states. So keeping this information in mind, we recorded data from anesthetized paralyzed cats in area 17 and 18 in response to natural image movies. So we wanted to develop a system identification model. So without going in the conventional way of just having a stimulus-driven pathway, now we have a parallel cortical state-driven pathway, which is going to capture the neural variability. And the input we give to the cortical state-driven pathway are LFP and MUA, so local field potentials and multi-unit activity. And the reason we are using this is because they have shown to vary depending on the brain state. And these modulatory effects from brain state go and additively modulate the stimulus-driven response to finally estimate the neural response. So how we predict, how we get the accuracy is by comparing what's estimated by the model to what we actually recorded from the neurons. And the measure we use is called VAF, variance accounted for value. So these are some key results. What we observed is that when we incorporate the brain state pathway, most of the neurons improved their accuracy. The scatter plot, the scatter plot here shows this clearly. In the x-axis, you can see the accuracy you get from just a stimulus-driven pathway, so without brain state effects. And y-axis shows the accuracy you can get from the full model. And as you can see, most of the neurons are above the unity line. And something interesting is that the yellow color data points, which are highly variable, they are the ones that shows the highest improvement. So this shows that neurons that are highly variable, the reason for this variability should be like the brain state effects. That's why when we incorporate them in our model, they shows the highest improvement in the accuracy. And another thing I didn't mention before is that the two neurons that I showed in the first slide, they were recorded simultaneously. So, but one neuron was highly variable, but the other one was not variable. And we wanted to know why this happens. So we went ahead and categorized neurons. And we found that depending on the category, the brain state effects can change. So we analyzed a lot of categories. And if you want to know, you can come to poster number 48, and we can discuss. Thank you.
Thank you very much. Up next, we have Charlotte Volk.
Hi, so I'm Charlotte. I'm a new master's student in Blake Richards' lab at McGill, and I'm presenting my undergraduate work with Shahab Bakhtiari today. So in generalization in visual learning varies across tasks, with easy visual tasks and training on easy visual tasks generalizing better to new contexts than hard visual tasks. And if we use a sequential curriculum, so starting with an easy visual task and progressing to harder visual tasks, this actually improves generalization on the harder task. So what we wanted to do was figure out why and how this sequential curriculum leads to improved generalization. So we modeled the visual system with a modified version of AlexNet that's pre-trained on object categorization on ImageNet data. And we fine-tuned our model on an orientation discrimination task where we have a target stimuli and a reference stimuli. And the model's job is to basically classify whether the target is rotated clockwise or counterclockwise from the reference. So we trained this model on two different training paradigms, a sequential curriculum where we started with an easy task and then progressed to a larger angle separation, and then progress to a more difficult task or a smaller angle separation. And we also had a non-sequential training paradigm where we trained the model only on the smallest angle separation or the hardest task. And we can see that the specificity is lower for the sequential model, which means that it generalizes better on the test condition on this hard task. So what is the mechanism for how this happens? So number one, the first training phase in the sequential curriculum recruits a low-dimensional readout subspace of neurons. So what is this readout subspace? Basically, we take the 100 neurons of the readout layer that have the highest absolute values of their weights. And what we do with those is we take their activations in response to 100 natural images, and it creates this activation matrix that we can then analyze. So if we take the first singular value of the activation matrix for models non-sequentially trained on only a single angle separation, we can see that the singular value, or the variance explained by this singular value, is higher for larger angle separations, so easier tasks. And basically what this implies is that the activation matrix is lower when the singular is lower dimensional when the singular value is higher. So what this implies is that a lower dimensional representation leads to better generalization. And then we compared the dimensionality of the sequential model's activation matrix and the non-sequential model, and using the effective rank, and we find that the sequential model leads to a lower dimensional readout subspace. And we can see this visually in the preferred visual features of the neurons that read out to these readout subspaces, where in the sequential model we have these groups of very visually similar features, while in the non-sequential model we don't see those groups. So we have that the first training phase sets this low dimensional subspace. The next part of this is that the second and subsequent training phases basically are able to piggyback off of this first phase, and they don't change the readout subspace very much. So we can see this on the PCA of the readout weights during training, where the initial step in the training basically sets the trajectory, and then this trajectory doesn't really change throughout the next steps of training. And we can also see that the actual locations of these 100 largest weight readout neurons don't actually change throughout training. Their weight is just increased. So what we're left with is that a sequential curriculum, learning curriculum, can help generalization by number one, in the first training phase, which is on an easy, more generalizable task. This leads to a lower dimensional readout subspace, and then subsequent tasks can use this more generalizable readout subspace, and they can piggyback off it. And basically this doesn't change the readout subspace, but it just increases the weight of the weights in this readout subspace, and that leads to better generalization on the hard task in the sequential learning curriculum. So if you have any questions, please feel free to come see me at my poster. It's number 52. Thank you.
Thank you very much, Charlotte. Next up, we have Tianyi Zhu.
Okay, hey guys, so my name is Tianyi, and I'm here to present my undergraduate research project. And so the task that we want to tackle at hand is basically called catastrophic forgetting. This is a common issue in models where when a model tries to learn new tasks, on new tasks, it forgets the knowledge of previously learned tasks. And so to put this into more perspective, imagine the MNIST classification data set. Now, if we were to divide this data set into 5 classes, the first one, 0, 1 digits, and then 2, 3 digits, 4, 5 digits, 6, 7, and 8, and 9. Now, in a standard linear SGD model, our performance is as such. I'm not sure how to point, but is as such. So the blue line represents the accuracy for the 0, 1 data set. And so our model learns how to classify 0, 1 very, very well at the start. But once it starts to switch the task from 0, 1 into 2 and 3, right? Our model starts to perform very well for classifying 2 and 3, but forgets the classification for 0, 1. So this problem is, this is the problem. And so what we have thought about is the S learning curve for humans. And so we as humans, we don't really learn linearly and forget linearly. Instead, we have this slowly learning period, followed by an exponential learning period, and then followed by a memory consolidation period. And so this really resembles a sigmoid graph, right? So what we have thought is that maybe instead of modeling our weight growth as linear, if we could model it as sigmoid, maybe it will help with remembering things. And this proves to be the case, as the 2 pictures that you can see on the left here, it's basically how our hidden layers looks like at the very end of the classification task. So after we have performed 0, 1, 2, 3, 4, 5, all the way to 8 and 9. And so for the linear weight growth model, it's very obvious that a lot of the features of the previous learned digits are missing from here. So there's no 0, there's no 1, there's no 2, there's no 3, there's no 4, and there's no 5. Whereas for the sigmoid model, right, we have this, we have digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. I have counted, yes. And so it really shows that this has, by changing this fundamental building block in our model, we can really achieve a remembering stage for our model. And so this is basically what we incorporated within our heavy learning model. And so these are the graphs that really shows the performances of SGD model and also Hebbian model. But then the first row represents the Hebbian model performance, second row SGD model performance, and then the first column is when Hebbian is paired up with sigmoid weight growth. The middle column is exponential weight growth. I should probably explain that, but it's very intuitive. Instead of a sigmoid, we just have this exponential learning curve, but also an exponential forgetting curve. And then the last one is linear. Now, how to read these graphs? The y-axis is the accuracy. The x-axis is the total number of samples seen. And then the blue line represents the test accuracy of task 1, which is basically classifying 0 and 1. Whereas the red is for task 2, yellow, task 3, etc. And so if we were to focus on the exponential graph, right, with Hebbian learning, now we can see that our model achieves a 80%, like above 80% accuracy very, very quickly. So 80% is basically the threshold that we set our model to switch tasks. And so once it achieves 80% accuracy, the blue line here, right, we switch to the red line, which is the training on 2 and 3 data set. Now then, we can see that, well, it learns very, very fast, but then it experiences catastrophic forgetting, where the blue line stays relatively close to 0 accuracy throughout the entirety of the task in the end. And so comparing that with Hebbian learning with sigmoid, we can see that the blue line, right, learns to a relatively high accuracy and then maintains this high accuracy throughout. And so this really shows that it really remembers this accuracy. And for linear, it does perform better than exponential, but it is also clear that it does experience a forgetting, where we can see with the yellow line and also the red line in the end. And this is basically just to show that like Hebbian with sigmoid is a good model, offers a good model performance. And we tested it with the stochastic gradient descent models. And while sigmoid does help mitigate a little bit for the stochastic gradient descent models, it does not perform as well as the Hebbian with sigmoid. And for exponential and linear, the results are very obvious. It's not very good. And that's it for my presentation.
Thank you very much. And for our last, but certainly not least, presentation of the day, put your hands together for Vincent Thibault.
So hi everyone, I'm Vincent Thibault. I'm a fourth-year PhD student in physics at Laval University with Patrick Desrosiers and Antoine Allard. So my project is the low-rank nature of connectomes and the reducibility of RNNs. So the brain is a complex system. It has a very high dimensionality. It is characterized by large-scale collective emergent phenomena such as learning, perception, neural synchronization. And to get insights on these spectacular phenomena, we can, for instance, take an animal model, extract the connectome, and take your favorite network model to model this connectome. So you end up with a weight matrix, and put that again in your favorite dynamical system, such as the Wilson-Cowan model. So you have a dynamics on a network. On the other hand, you can also have start with time series, use a RNN, and get a learned weight matrix. And what you end up with, again, it's a high-dimensional dynamical system on a network. The problem is that at that point, this is still a very hard thing to get insight about. It's characterized by a lot of differential equations. So what people do in general, they reduce the dimension. And to do that, we have observed in the community that in the literature that people are making very often a low-rank hypothesis on the weight matrix W that describe the interactions between the elements in the system. So the goal of the project was really to question the validity of such hypothesis and especially to verify it for real connectomes. So to do that, so a network can be represented as a real matrix, and a real matrix can be decomposed with singular value decomposition. I was happy that Charlotte talked about singular values, because in the end, singular values, basically the number of significant singular values will inform you about the dimension of your matrix, basically. And so the question at that point was, for connectomes, how fast are singular values decreasing? And so if, of course, if the singular values are decreasing very fast, you will have low effective ranks, and on the other hand, if they decrease, for instance, linearly, well, you will have high effective ranks. So we have gathered about 700 real networks, and among them there were 30 connectomes that we could find at that time, and we indeed find that the singular values were decreasing rather fast, as you can see for the Drosophila, for instance. And this implies that the effective ranks for these connectomes are also low. But what's the impact on artificial neuronal dynamics? What is their effective dimension? Can we predict their large-scale emergent properties? Well, some mathematical considerations allow us to tell ourselves that we might be able to do it, because the activity of the neurons can be encoded in a vector that lives in a very high-dimensional space. But when you multiply this vector by a matrix W that has a low effective rank, then the vector Wx will live in an effectively low dimensional subspace. And that's what we observe. In fact, if you take the connectome of the C. elegans and you put that into the Wilson-Cohen dynamics, you will be, we were able to predict the global activity at equilibrium with rather few number equations compared to the original size of the connectome. And on the other hand, you can also study the RNN dynamics on a learned weight matrix, and we could predict complex limit cycles. And we also observed that RNNs can be exactly reduced, which was pretty surprising to learn this. So all in all, despite the very high dimensionality of the brain and complex system in general, we might be able to find transformations in lower dimensional space so that we can get insights on emergent phenomena. So if you want more information, the paper is published. The reference is just above. So thank you.
Thank you very much, Vincent, and that brings our lightning talk session to a close. Just before you head out the door, I'd like to let you know that there will be donuts in the Hall d'Honneur in line with our marketing. And so I'd like to thank all of the students, I'd like to thank Maine for showcasing student efforts, and thank all of you for being here today.